And we once more turn back to the technical questions. Peter will give us some recommendations for lenses.
So, to be the last man standing here is a very special honor for me. Thank you for your broad attention on a very basic topic. This one? Or this one? Okay, yeah. So, just to jump into our topic, high-speed lenses. This is the equipment of my first video observation for Meteor. Looks quite unusual for you, maybe. This is, where's the laser? Yeah. This is a professional film camera, 35 millimeter, so APS-C equivalent with a high-speed lens. You see here, well-known German manufacturer, wide angle, 18 millimeters, with a speed of 1.2. Why? Briefly spoken, for meteors, speed requires speed. So the meteor has an angular speed in the image, and that requires a high speed of the lens that we can detect motion, because we want to decrease the integration time. When we make a photo, we have a streak of the meteor. When we have a video, we have small streaks of the video. And the higher the speed of the lens, the smaller the streaks in the image, in the frames. Okay, here we keep this value in mind. That means entry pupil and the diameter of the entry pupil of this lens here is 15 millimeter, so like that. This is much, or that is only very small compared to another value that we have to take into account. So why are there high-speed lenses on the market? The market is not, the mass market on photo lenses is not about meteors. The mass market is dominated by this. People want to photograph people. So people require people, and often they want to concentrate on the people, especially on the face, on the expression, and that requires a shallow depth of field. So the main motive to construct high-speed lenses in the mass market for photographic and also cinematographic lenses is the portrait with a shallow depth of field. By the way, in this hotel, you have nice images in every room, and look at the depth of field and imagine what the speed of the lens must have been. A shallow depth of field is produced by an unsharp area in the image before or behind the focused object. And there you can see some kind of a blur. And here, for example, you can see it very well. This blur is also has a certain figure that is typical for the lens and the lens construction, and this is so-called bokeh. Bokeh is very important for the aesthetics of the unsharp part of the image. So we want the usual public wants a shallow depth of field with a pleasing bokeh, whatever that is. When did it start for large, I'm not talking about small video cameras, but of classic photographic camera. And this is an early advertisement from Lights in the year 1961. By the way, that's also the year where I was born. And I was born on the day when the first man was shot into space. His name was Yuri Gagarin. From a country that doesn't exist anymore. So lots to talk year 61. And there, in a way, it started because this was, this was one solution for the first time, aspherical lenses. in English it's not that precise. A lens and a lens can be confused. So you have, of course, in this Objektiv, as we say in German, several lenses. And here they are not only round-shaped, but also aspherical. And that was the key. In the same year, Canon came up with an impressive speed of less than 1. Some people think that that is a natural barrier, but it isn't. From today, you have to say only 7 elements in 5 groups. This lens here has 15 lenses in 12 groups. But nevertheless, these are really high-speed lenses. What was the key? High refractive glass, new sorts of glass. And by the way, here you see the yellowish appearance with elements like strontium and something like that. You try to avoid that today, but at that time people were more daring. So Zeiss company, there were some guys that were kind of annoyed about all the rumor about high-speed lenses, and they constructed this, and they demonstrated it on Photokina. I was not at Photokina 1966, but they demonstrated at Photokina the Super Q Giganta with an impressive speed of 0.33. But it turns out that in German, the Q stands for Quatsch. It didn't work, it was just a mocking, because this is a condenser lens, and when you see it from the side, it's like that. Forget that, that's just fake. But it was sold, one example was sold for 60,000 euro on I think it was Sotheby's or so. Very seriously is this lens, because it's world famous, and you can ask every film student what was the fastest lens, and he said, yeah, I know. It was Stanley Kubrick using this for this really impressive candlelight scenes that were shot in real candlelight only. In the film Barry Lyndon in 1975. Go to YouTube and you find pieces, very impressive. But if you have a close look to the candles, you see there are special candles. By the way, the ISO of this film of that days was 250. So that was the main reason that at that time the sensitivity was so low that you really needed any photon you can grab from this candlelight. And it was done with a Zeiss planar that Zeiss developed for NASA. And I think there was 15 pieces manufactured, and 2 of them were acquired by John Alcott for this film. And it was 0.7 to 50 millimeter focal length. So in astronomy, we do not have a depth of field. Everything is in focus, hopefully, and so we do not see the bokeh. Okay, so that is a good message. We don't care for the bokeh, usually, and we don't care for the depth of field. But what we have to deal with is the light distribution, for example, from the center to the corner. That's very interesting. And so the speed of a lens might be very good in the center, but the fall off to the corner has to be taken into account, because we don't want to do too much flat fielding. That comes with other disadvantages. Okay. Briefly, relevant optical parameters, the focal length. Okay, that's the distance between the primary plane of the lens and the focal point. And that gives you the demagnification of the image. We strongly demagnify our objects. Yeah, we put the whole universe on this little chip. So we strongly demagnify. This beamer, for example, here does the opposite. It magnifies strongly, and the lens is more or less of the same construction due to the nice fact that the path of the light can be reversed, and the same lens, more or less the same type of lens, can be used for projection as well. That gives us hope, because from projection we can acquire some very high-speed lenses. The image circle, of course, any sensor is limited by its diagonal. It has the image circle of the lens is round shaped. The sensor is usually edge shaped and has to fit into it. Am I running out of time? 1 minute? Okay, then I ignore that. The field of view. Pardon? Okay, thank you. The field of view is, is of course very important for us, because when we catch meteors, we want a high field of view. And the aperture size, that's the real thing that we want. The size of the aperture is simply that what is going, if you make this little experiment every year. So you have a bunch of light rays. You have an aperture. And the aperture tells you what goes through and what is abandoned. So only these light rays come to your sensor. If the aperture is large, you have more light rays. If the aperture is small, you have less. But the f-stop of the lens, and that correlates with the speed is nothing more than the minimum f-stop, is the relation between the quotient between the focal length and the diameter of the f-stop. So that's the reason why, of course, it's the area, not the diameter, that is proportional to the amount of light. So with the circle formula, you get a relation that goes with a square root 2 factor of the f-stops. Okay, I jumped that for time reasons. So that puts us into a dilemma. I call it the Meteor's high-speed dilemma, to make a dramatic effect here and a big takeaway for you all. Faint meteors, we want large aperture. Even bigger, telescopes, of course. But usually this comes with higher focal length due to the speed. That means a smaller field of view, and that means less meteors. And this is quite practical. I presented this already, I think, 2 times. And I have a wide-angle lens, a medium-angle lens, and telephoto with impressive aperture of more than 140 millimeters. But the number of meteors due to the field is decreasing. The aperture is rising and the number of meteors is decreasing because you limit your field. So that's the dilemma, aperture versus field. And that leads us to high speed, small focal length. Thank you, Zirko, for this photo. This is an early example of high-speed lenses for small sensor cameras, image intensified. You see it's an analog photo, and these ray stars are from projection systems as well, and quite impressive. If you see the entry pupils, it's really big holes that collect light. And I used these Cine lenses for larger sensors. It becomes more and more complicated to build high-speed lenses. So with a full format camera like the Sony Alpha 7S, a 50 millimeter lens here you can still call a high-speed lens. And especially the 84 provides you with entry pupils of 35 up to 60 millimeter diameter, and that's some square millimeters of. One idea is good to accumulate apertures, but not focal length. So you combine different cameras, and everyone should be familiar with a site like that, because that's what AllSky 7 does in another way. And this example we built, Matthias Knülle and I, we built this camera battery with analog T70 SLRs with 50 millimeter lenses. And then you can combine the apertures, and I made a brief calculation. If you have an overlap of about 75%, So you lose some of the efficiency. But if you take 13 cameras with each an aperture of a diameter of 27.8 millimeter, you get an overall effective aperture of about 87 millimeters for nearly all sky. So that's a way to improve, to overgo that dilemma. And that's what All Sky 7 does as well. So I made a calculation about the effective aperture of All Sky 7, ignoring the 8th camera. This is the values that you find for that system. You have an overlap of only, I have to say, 81.2%. And if you make the calculation of the collecting all the area of the 7 cameras and reducing it with 81%, and then go back to the circle formula for the entry pupil, you find 8.5 millimeters. That does not sound too much, but it's much better than the 4 millimeter aperture of the single camera. And you saw that already. So this is a fisheye lens. So now it's, where's Mike? You don't like them. You have your reasons, but you have to say, a fisheye lens has one big advantage. It has nearly, by its construction, nearly no fall off from the center to the corner. On the other hand side, it's not possible to build what we call high-speed lens because, as a fisheye, because there are optical limits due to the refraction and the radii of the glasses. So this is a 2.8 fisheye lens. Normally you would say that it's not high speed, but for fisheye it is high speed. That's the reason why it deserves a place here today. And the combined aperture here, I made the calculations, only 6.4 millimeters, so that's less than All Sky 7. Yes, of course, it's only 2 lenses. But the resolution is much higher. But so you have to, I mean, that's not a concurrence for All Sky 7, it's an experiment. Low speed, yes, but uniform brightness. So also a uniform distortion because the optical axes are parallel, they are not tilted to each other. Okay, so it's a little bit a pet shop of my high-speed lenses. And the orange ones are from projection, the white ones are from photography, and these I have here. And these yellow ones are for film. For example, here, nicely made 16 millimeter lens from the 1950s. So is there a physical speed limit? Yes, it is, as long as we use refractive elements as lenses. It is, and it depends on the sensor size. So I found here, thank you to I think Zirko gave me that indication. This guy examined high-speed lenses, and I found one that was 0.57. I don't know how the quality is because a quality of a lens is multidimensional. What you dream is something like that. Yeah, dream on. You will not get it for your money. What you get as a real lens that you can buy, for example, something that lacks of aperture, but has a good quality in resolution and contrast, but sacrifices, for example, on the distortion side, you accept some distortion, or the uniformity of the resolution, you accept there's some kind of a resolution sharpness fall up from the center to the corner. So this is a high-speed lens. Very typically, you have a large aperture, but low uniformity of brightness, maybe no good uniformity of resolution, and some lacks of image planarity, which is also not very funny for astronomy, and things like that. So that's the main reason. I would strongly recommend to do a very simple test if you are unsure if your lens works very well. So also for you to test it, take Sirius or any bright star, make 2 photos, one with a star in the center, then the star in the corner. and that is what you get. And this is the comparison between this Sony and this Canon, and the size in the middle is missing. Even in the center, the new modern lens provides a strong advantage over the old-fashioned lenses. But in the corner, it's more dramatic. This is the figure for the Sony, and this condor-like appearances of the star is what you have when you have coma and all astigmatismus and so on and so on. And all this light here, of course, surely is not there where it should be. So also resolution counts, and I come to the end. Aperture counts, but also field of view. There is no magic stick. If in lens design you sacrifice everything for a large aperture, then you have surely shortcomings on the other parameters, and you get a very unbalanced image. So a balanced lens is better than an unbalanced. And lenses with good correction of all image quality parameters are quite costly. So we are here above €2,000, but it's worth the price. So for astronomical ultra wide field imaging, such as meteor observation, especially all sky, multi-aperture systems are highly interesting. So I'm racing a little bit, but thank you so much for your attention. Okay, the exam is in 2 weeks in the small room. And
thanks a lot for your talk and for the advertisement of the correct lenses and the factor.
There are others as well. That's just my choice. Zeiss has very good ones, and other manufacturers as well.
Okay, as it is the last talk of the session, I think people who want to ask details should rather contact you and have a look here in order to be on time with those who perhaps have to leave. So it's the point to close this session, but the conference will be closed now by the president. Thanks once more, Peter, for your talk, and thank you.